In this lecture, I'm going to talk about householder transformations. And first, as usual, I would like to say a couple words about the person who invented this method. And this person is Alston Householder. He was an American mathematician who got his PhD degree at the University of Chicago. And his dissertation topic was related to the calculus of variations. After receiving his PhD degree, he concentrated on mathematical biology. Also, he was president of a Society for Industrial and Applied Mathematics. Today we are going to talk about his contribution into numerical analysis and especially about his method, householder transformation, or another name is householder reflection method. First, let me start our discussion from describing the general idea of this method. Or to be more precise, let me discuss the main purpose of using this method. As you remember, during last lectures we talked about how to find the eigenvalues of a particular matrix A. And right now we still have the same goal. We want to find the eigenvalues of matrix A. And there is one method which calls QR method. And we are going to study this method in a few lectures. But as a starting point, this method uses a three-diagonal matrix. And in the end, it allows us to get nearly diagonal matrix, and these diagonal entries will be exactly approximations for our eigenvalues of our original matrix A. But in order to start using this method, we need to transform our original matrix A into three-diagonal form. And this is exactly why we are using householder transformation. This method allows us to transform symmetric matrix A into three-diagonal form. So, let's say we have matrix A n by n, which is symmetric, and we apply a sequence of householder reflections or householder transformations in order to convert our original matrix A into three-diagonal matrix as a result of n-2 transformations. And as a result of this method, we will get three-diagonal matrix. What it means? That first you deal with symmetric matrix. After the first step, you will get zeros in the first column and row. Then, after the sequence of householder transformations, you will get matrix that contains non-zero entries on three diagonals, and the rest entries will be zero. Just one remark. Just pay attention that when you implement householder transformations, you should notice that let's say in 99% cases, you won't get exactly zeros. You will get small values. These values can be different. Sometimes you might get something like 10 power minus 6 or 10 power minus 9, but under certain conditions it can be considered as 0 and you can neglect them. So, next step. In order to apply householder transformation, we will use this theorem what I covered when I talked about orthogonal matrices. And this theorem states that the n by n matrix A is symmetric if and only if there exists a diagonal matrix D and orthogonal matrix Q with the property that A equals to the product matrix Q multiplied by diagonal matrix D and multiplied by transposed matrix Q. And we are going to use this theorem today in order to show how householder transformations work. So here there is the definition. Let W be a vector from Rn with a property that transposed vector W multiplied on W equals to 1. The n by n matrix P equals to the difference between identity matrix and doubled product vector W and transposed vector W is called a householder transformation, or sometimes we call P householder matrix. You can use any notation. First, let me formulate the following theorem. A householder transformation P, which is equal to the difference between identity matrix and doubled product of vector W and transposed vector W, is symmetric and orthogonal. So the transposed householder matrix P equals to the original matrix P. How we can prove it? First, I would like to say that you should recall the chapter 7 from your textbook, where matrices were discussed first time and where all properties were discussed as well. So let's consider the product of vector W and transposed vector W, and let's transpose it. Then by using matrix properties, we should recall that transposed vector from transposed W equals to the original W, and this is the case. Then we can consider householder transformation. Here, by definition of householder transformation, we can write P is householder transformation. We take transpose matrix, we consider transposed matrix, and since we just proved, let's say, equation 1, apply equation 1 here. Here we consider this product, and we can say that now we see clearly that transposed matrix P equals to the original matrix P. The next step, again by the definition of householder transformation, the product between transposed vector W and vector W equals to 1. Let's keep it in mind and consider product of our matrix P and transposed matrix P. And we already proved that it equals to this. Now we can simply multiply them, and by performing simple calculations and by performing if we recall associativity property as well, we can say that this product equals to identity matrix. By summarizing all our calculations, we can say that our inverse matrix P equals to transposed matrix P and equals to the original matrix P. And this is exactly what we try to prove. The theorem is proved. Now let's consider the method. Let's start our discussion about householder method. This method begins by determining a transformation P1 with the property that matrix A, let's say 2, should be equal to the product P1 matrix A and once again P1. As a consequence, we will get 0 entries in the first column for j from 3 to n. As I showed you on previous slides, if we have matrix with certain entries, starting from j equals to 3, we will get 0 after the first step. Because we have symmetric matrix, we have zeros here as well. And here we have certain numbers. Right now, it's just non-zero entries. This is what we will get after the first step. And here by symmetry. So, now choose vector W. Choose W. W1, Wn, these are just components. And we choose this vector such that the product of a transposed vector W multiplied by original vector W equals to 1. In addition, second approximation for our matrix A, which is equal to the product of householder transformation from previous step or from previous iteration multiplied by original matrix A and again multiplied by the householder transformation from previous step equals to this product, and it implies that entries A11 from the second approximation matrix equals to the A11 to the original matrix, and entries for the first column starting from j equals to 3 to n equals to 0. Setting W1, its first component of our vector W, setting W1 to 0 ensures that we have this equality. Moreover, if we recall our householder transformation, which is here, we can say that it should satisfy this expression, where alpha is a number that we are going to define slightly later. Now what we are going to do, we are going to slightly simplify notation. We introduce W hat and Y hat. These are just two auxiliary values what we are going to use in order to make our calculations more clear. And what we are going to introduce, W hat, is going to be vector from the space n-1. Dimension will be one less than on previous step. And Y hat also has dimension n-1 from R n-1 space. As a consequence, P hat it's going to be household transformation, but P hat also will be n-1 by n-1 matrix. And by definition of household transformation, P hat is going to be the difference between identity matrix n-1 dimension as well minus doubled product of vector W hat, not W. And our equation, let's say equation 2, becomes, let's say equation 2, we can write as follows. So here we have our household transformation, first household transformation, multiplied by entries from the first column from matrix A, and we will get zeros here and here, first column and first row. We will get matrix P hat or household transformation, which is going to have size n-1 and multiplied by this vector where A11 is the first entry, and then vector Y consists of also entries from matrix A. So as a result, we will get vector where we will have A11 non-zero entry, number alpha, we will discuss it soon, and the rest will be just zeros. And if we just write more precisely this product P hat Y hat, it's just clarification. How to get this final answer. Let's introduce new variable R, which is equal to the product of transposed vector W hat and vector Y hat. Then we have the following expression in this form. We write it in component form. From previous slide, we know that vector Y hat has components A21, A31, A and 1. Also, we define this product as R, and vector W has components W2, W3, Wn. and this is how we can write it. Based on that expression, we can find all wi once we know alpha and a. Now the question how to define alpha and how to define a. Let's try to do it. First, we equate left and right hand sides from our expression 3. We will get, this is first row, and this is all our rows, since all entries on the left side are 0. This is for j from 3 to n. So let's simplify slightly our expressions. Let's move this product on the left side and the rest entries from matrix A and alpha leave on the right hand side. Then what we are going to do, we are going to square both sides of each equation and add corresponding terms. How it should look like, we should square it first both left and right hand side, then we add them, and this is the expression what we are going to get. Since this product of transposed vector w and original vector w equals to 1, and since vector w not vector component of first component of the vector w equals to 0, we can say that this sum of the components of vector w, squared components, equals to 1, and j starts from 2. So we just obtained this formula from previous slide, and now we just slightly simplify our expression by opening these brackets and square our expression. Then we use another expression from previous slide, and by recalling that p is orthogonal, we can use this fact and write down the following expression if we square our alpha and write it down slightly differently using this expression. We can get that alpha squared equals to the product of a transposed vector y hat and the original vector y hat. As a consequence, we can write down alpha squared using components of vector y. And as a next step, we can substitute this result, let's say result 4, in our equation from here. So if we do that, we can notice that we can simply divide on 2, and this is our resulting expression. In order to ensure that a squared equals to 0 only when a equals to 0, we should choose our parameter alpha using this formula. This is our formula for parameter alpha. And if we explicitly plug alpha into our, let's say, formula 5, we will get this expression. Once we chose parameter alpha and parameter a, we can solve equations in the blue box and find all components of our vector W. Now let's summarize the choice of our householder transformation at step 1. Well, we define parameter alpha. When we compute parameter a, how to do it I showed you on previous slides. When we assign first component of vector W, W1 equals to 0. When we compute the rest components of vector W using these formulas. And our matrix A, the next approximation for matrix A is going to be the product of householder transformation multiplied on original matrix A and multiplied again on matrix P. And the resulting matrix after the first step, after first householder reflection, will be matrix with 0 entries in the first column of the matrix, starting from the third row. And because we deal with symmetric matrix, we have 0 entries starting from the third column as well. But the rest just non-zero entries. Once we found our P1 householder matrix and we computed the next approximation for our matrix A, A2, and obtained first column and first row 0 entries, where we expected, we can repeat this process for our case from 2 to n minus 2 as follows. And below I provide you just generalization of formulas, what I wrote you and what I derived for you on previous slides. Just instead of 2 and 1, we should have k plus 1, k index. And here it means iteration, not power. And it means that we consider we take k entries from matrix A, for example, in order to compute, let's say, third matrix, third approximation, let's say it's k plus 1. K plus 1 equals to 3, then we should take entries from previous iteration from A2, not from the original matrix. We should take entries from this matrix, from if k equals 2. We plug here these entries. So we can find alpha, we can find A with similar, and just do not forget, this is just a reminder from which matrix we should take these entries. At the same time, components of vector W should be equal to 0 from 1 to k for kth iteration. So, and the rest components can be computed using these formulas. And just remember, do not forget that every time you use previous iteration, matrix A from previous iteration, and you compute householder transformation, at every step, and your final matrix k plus 1 will be product of householder transformation pk multiplied on ak, not the original matrix, and again multiplied on householder transformation from previous iteration. We use kth iteration here in order to compute k plus 1 iteration. As a result, we see that we have 0 entries here, and our goal is to get 3 diagonal matrix. So we can continue this process, and this is the most general formula how we can compute an-1 matrix, and we will get 3 diagonal and symmetric matrix, and after that we will be able to apply QR method to find our eigenvalues, what we want. And actually 3 diagonal matrix was our goal, and this goal was achieved. It's done. Now let's solve an example.